Welcome to another IB Environmental Systems and Societies video. In this video, I'm going to walk you through the Criterion E of your ESS internal assessment. This criterion covers two closely connected things, your analysis and your conclusion. These two sections are where all the hard work you did collecting and processing data finally comes together. By the end of the video, you'll know exactly what examiners are looking for and how to give it to them. So let's get into it. Before we go into the details, here's the big picture. Criterion E asks you to do three things. First, your interpretation of the data must connect directly to your research question. Second, you need to find and explain the patterns in your data, not just point them out, but actually explain what they mean. And third, your conclusion has to be supported by the evidence that you collected. Notice that word, supported. Your conclusion can't just be something that you believe. It has to grow out of your data. So keep these three things in mind as we go through each part of Criterion E. Now let's look at how this criterion is actually marked. The marks range from 0 to 6, and the difference between a low score and a high score comes down to one key word, explain. A student who earns 1 or 2 marks has identified patterns in the data. A student earning 3 or 4 marks has described those patterns and connected them to bias, reliability, validity, and uncertainty. But a student earning 5 or 6 marks has explained all the patterns, and they've fully addressed all 4 of those measures. So the goal is always to go beyond just noticing something in your data, and you need to explain why it happens and what it means for your research question. So what exactly are patterns and trends? A pattern is a feature that repeats in your data. For example, if nitrate levels are consistently higher near agricultural land than near forests, that's a pattern. A trend is a change over time or across a range of conditions, like nitrate levels increasing as you move away from forest and towards farmland. The important thing is you don't just say, there's a pattern here. You need to explain what's causing that pattern. Why are the values higher in one place? What environmental processes explain it? Then you connect that explanation back to your research question. For example, in this graph showing atmospheric CO2 concentration, the pattern is that carbon dioxide levels spike every year during winter in the northern hemisphere, and they fall again during northern summer. That's because photosynthesis drops when deciduous forests go dormant during the winter, and that slows the uptake of CO2 from the atmosphere. When those forests start actively growing again during the spring and the summer, they pull more CO2 out of the atmosphere through photosynthesis. The overall trend is an increase in atmospheric CO2 concentrations due to ongoing human activities like fossil fuel combustion, deforestation, and land use change. Your data should be telling a story, and your job in the analysis is to narrate that story clearly. One part of the analysis that students often skip is bias. Bias happens when your data collection method causes your results to lean or skew in one direction, not because of what's actually happening in the environment, because of how you collected the data. For example, if you only surveyed visitors to a park in the morning, your results might not reflect the behavior of afternoon visitors. That's a form of sampling bias. In your analysis, you need to identify any sources of bias in your investigation and explain how that bias might affect your conclusions. Acknowledging bias doesn't weaken your investigation. It actually shows the examiner that you understand the limits of your method. Reliability is a straightforward concept, but it's easy to miss. Ask yourself, if another student repeated this exact investigation with the same method and you weren't there to explain it to them, would they get similar results? If the answer is probably yes, your method is pretty reliable. If the answer is maybe not, you need to explain why. Common factors that reduce reliability include changing weather conditions between sampling days, equipment that doesn't work consistently, or measuring sites that changed between visits. For example, if a heavy rainstorm happened 2 days before you sampled soil moisture at some of your sites, those readings are not going to be consistent with all of the other sites that you sampled. Identifying these issues and explaining how they affect your results shows strong scientific thinking. Validity asks a different question. Are you actually measuring what you intended to measure? This connects directly to your research question. If your research question is about the effect of acid rain on a lake and you measured water pH, then your method has high validity because pH, of course, directly measures acidity. But if you counted bird species to measure biodiversity, you've measured species richness, not species evenness. This means that a biodiversity index like Simpson's reciprocal index can't be fully calculated, and that limits the validity of your biodiversity conclusions. In your analysis, you want to explain what your measurements do well and where they fall short. Every measurement you take has some degree of uncertainty. That's a range of possible error. If your thermometer measures to plus or minus a half a degree Celsius, that uncertainty matters when the difference between two sites is only 3/10 of a degree. In that case, you can't be confident that the difference is real. You always report the uncertainty of your measurements, and then you explain how that uncertainty affects your confidence in the conclusion. You also want to distinguish between random errors, those are unpredictable variations like wind affecting your readings, and systematic errors. Systematic errors are consistent problems like a scale that always reads 2 grams too high. It's something that affects every measurement you take. So here's where students make another common mistake. They write separate paragraphs labeled bias, reliability, validity, and uncertainty. You can do that because it makes it really easy for the examiners to find those things, but you don't need to do that. Instead, you want to weave all 4 of these things together into 1 or 2 integrated paragraphs that tell a narrative. The example on the slide shows you how to do this. It starts by identifying a clear trend in the data. Soil nitrate increasing from 15 parts per million in the forest to 45 parts per million near agricultural fields. It then connects that trend to the research question, and it evaluates the reliability of the method, it addresses validity, quantifies the uncertainty, and it ends with a discussion of sampling bias. Notice how it flows naturally. That's what strong scientific writing looks like. You're not just going through and ticking things off a box. And this part of your IA serves as a great segue or a transition point because you can use these 4 elements as a basis for the improvements to your investigation. It sets the stage for your evaluation in the Criterion F section that comes next. Now let's talk about the conclusion. Your conclusion is not the end of your IA. Your conclusion is the final direct answer to the research question. The marking criteria here are also on a 6-point scale. 5 or 6 marks go to the conclusions that fully address the research question, and they're completely supported by the analysis. You'll get 3 or 4 marks to go to a conclusion that addresses the question, but are only partially supported by that analysis. And 1 or 2 marks are for conclusions that either miss the research question entirely or aren't backed up by the analysis. The most important thing to understand is that your conclusion can't introduce new ideas. It must come away from what your data already showed. When you write your conclusion, you always start by restating your research question, but probably in a new way, not word for word. Then you want to give a clear, specific answer backed by numbers. Compare the weak and strong examples from this slide. The weak version just says lead pollution is a problem in cities. That may be factually true, but it doesn't answer the research question. The strong version states that soil lead concentration decreased from 85 parts per million at 5 meters from the road to 22 parts per million at 50 meters from the road, and that this shows distance significantly reduces lead pollution exposure. The difference here is specificity. Use your actual data values from the data that you collected in the field. Use precise language. Answer the question that was asked. Your conclusion also needs to loop back to the 4 measures from your analysis: reliability, validity, uncertainty, and bias. Look at this example on the slide again. The biodiversity index result is stated clearly. The conclusion is connected to the hypothesis about logging and species diversity, and then the reliability of the quadrat sampling is confirmed. Validity is addressed by noting that only plant diversity was measured. Uncertainty is used to confirm that the difference between sites is meaningful, and the potential sampling bias from dry season data collection is also acknowledged. That's a complete, high-scoring conclusion because it tells the examiner not just what you found, but how confident you are in your findings. So let's close with a checklist. Strong Criterion E work means that all patterns in your process data are identified and explained. It means you've performed appropriate statistical analyses. It means reliability, validity, bias, and uncertainty are all discussed. It means your conclusion statement directly answers your research question, and it also means that your conclusion is supported by evidence from your analysis. 2 words should guide everything you write in this section, and frankly, these 2 words should probably apply to everything you do in the IA. Precise and concise. Say exactly what you mean and say it without unnecessary words. That combination will serve you well, not just in the internal assessment, but in all of your ESS work. Remember, your data already has a story to tell. Your job is to explain it clearly and succinctly. Good luck with your IA, and until next time, happy learning.